Good afternoon, everyone. Thank you for being here. I hope you got your good snack. I'm Reva. I'm a postdoc at CCSE. And today I'll be talking about our ongoing work on modeling pulsar magnetospheres using WarpX, which is funded by ECP. I'm going to start with what is a pulsar. Pulsars are rapidly rotating neutron stars that were born after they are supernova remnants, and they are rapidly rotating and highly magnetized. That is, after the core collapse, it's reduced to about 10 to 12 kilometers is its radius. That's the distance from here to Oakland. The mass is 1.5 times the solar mass. That is, if we were to take 1 spoon of pulsar, it's going to weigh as much as Mount Everest. And its period is about 1 millisecond to 1 second. It rotates about 700 times per second. Mark is still not buying it. And it's highly magnetized. So okay. They're rotating rapidly and they're highly magnetized, but why do we care about it, right? They have this very well-defined period, which makes them galactic clocks. And what I find most interesting about this is that we also used pulsars to communicate with extraterrestrial intelligence, or try to communicate with extraterrestrial intelligence, by sending this picture on Pioneer 10 spacecraft showing our position with respect to the sun and 14 pulsars. That's how incredible these objects are. But after its discovery in 1967, more than 2,000 have been discovered, and we still don't understand the fundamental question: how does it emit light? There are electromagnetic processes because of the strong magnetic field and the rapid rotation that accelerate particles, and it emits a beam of light. This beam of light, as the pulsar is rotating, when it sweeps by Earth, it's going to get detected as a pulse. And we don't understand what causes that light radiation. In order to understand this, we need to perform first principle simulations, understand what is the composition of the magnetosphere, that is the region around the pulsar. The method of choice for these kind of first principle simulations is electromagnetic particle in cell. This method is pretty straightforward. We have our simulation domain, and we represent particles, a plasma, as computational particles, where each computational particle represents large number of real electrons and positrons. And the way this works is these electrons and positrons will, in every time step, they're going to deposit charge on the grid, charge and current on the grid, and then instantaneous electric and magnetic fields are computed by solving Maxwell's equation. Once we do the field solve, the forces due to the electric and magnetic fields are gathered back to the particles, and the particles are pushed, and then they again deposit charge. So that is one loop in the particle in cell approach. Before we go on, I just want to quickly mention here that we do FDTD, which is finite difference time domain. This requires that our cell size must be less than the skin depth, or the smallest resolution that we need to resolve. The smallest length scale that we need to resolve. For a pulsar, which is 10 to 12 kilometers, the smallest length scale is 6 orders of magnitude smaller. But we want to understand what's happening around the pulsar, which means that if we were to do the simulation, we would need those many number of cells, 10 million cells in each direction. With a uniform grid, that is impossible. And so typically what is done is we scale down the problem. What I mean by that is we scale down this ratio of the radius of the star and the smallest length scale. But by doing that, we are changing the physics of our simulation, because we bring down the magnetic field, and that's going to affect our predictions from the simulation. But if we need to understand what is the effect of that scaling on the electromagnetic radiation, we need to be able to perform simulations. So typically, in the literature, people have gone up to about 10⁻⁻3. We want to go as close to the real scale as possible. So if we can go one scale up and find out what is the difference in that electromagnetic radiation, that's going to be good. In order to do this, we need to perform high performance particle in cell simulations, and we turn towards Exascale and we turn towards WARP-X and AMR-X. WARP-X is an electromagnetic particle in cell code that's been primarily built to perform particle accelerator simulations. But we want to extend it for astroplasma simulations. And the reason why we like WARP-X is because it's got all of these advanced features to perform particle in cell simulations. Of course, we are working right now on extending it, and the communications between the different subdomains and the AMR aspect is handled by AMR-X. Of course, we have done scaling studies for WARP-X on Summit for its primary application of particle accelerator simulations. And what I show here on the left is weak scaling studies. So as we increase the size of the problem and proportionally increase the number of nodes that we're using, does the time per iteration remain the same? That would be ideal, and we are very close to ideal for simulation with mesh refinement. And our comparison of WARP-X scaling with ideal for strong scaling studies are also very encouraging.
Are the bottom axis the same in both graphs?
I beg your pardon?
There's no bottom labels in it.
Oh, sorry. Yes. Yes. On both the graphs, the number of nodes, the x-axis is the number of nodes. Thank you for the question. And so we have our problem, we have WARP-X, and we want to extend it for pulsar, for studying pulsar magnetospheres. I'm going to go step by step as to what models we want to include and for what physical processes. So we have a rotating pulsar with a dipole magnetic field. Because of its rotation in a dipole magnetic field, very similar to Faraday's disk, its charges the charges inside are going to separate. And that charge separation is going to then lead to a very strong electric field. It's called a poloidal electric field between the pole and the equator. That electric field is so high that it's going to extract these electrons from the poles and lead to radiation. So we are not modeling the entire star. That's what Dawn does and Doreen does. We want to understand what happens in the magnetosphere based on our question of how does it emit light. So instead of modeling what happens inside the star, since it's well known that this charge is going to separate, we want to start with, let's do particle injection at the surface for modeling that electron extraction at the pole. And as these electrons get extracted and they start moving along these curved beefy lines, due to curvature radiation, they're going to emit gamma ray photons. These gamma ray photons, in the presence of a strong electric field, will then emit pairs. These pairs, again, there's another electron that's generated. It's going to emit curvature radiation, gamma ray photons, and a cascade of these pairs are then generated that fills up the magnetosphere with plasma, and then that's going to interact with this rotating pulsar and lead to electromagnetic radiation. A similar process also happens along these curved beefy lines in the equatorial plane, and that's what builds up plasma in this along this red line, which we call as the current sheet. So now we have dense plasma in this very thin region that already shouts out mesh refinement. And along with that, this pulsar is rotating, which means that at every time step, the location of this dense red line is going to rotate, and we need to perform dynamic mesh refinement. So that's our third step. We're a big fan of validating everything as soon as we implement it. So the first thing that we're going to do is particle injection, and we're going to verify and validate whether the particle injection is correct. In order to do that, we start with, there's no magnetosphere, there's no plasma around. Let's start with a pulsar in vacuum. The theory for vacuum is very well known. It was developed in 1969, within 2 years after pulsars were discovered. And for a pulsar with a dipole magnetic field that's rotating, like I've mentioned before, charges separate. This quadrupolar charge separation leads to a quadrupolar electric field. What I want to emphasize here is that this is R theta and ER, E theta, E phi. There is no E field along the toroidal direction. So it's poloidal and it's radial. And what we're going to, and the way we set up this problem is we have a pulsar, a sphere that's sitting in our cubic domain, 3-dimensional domain, and we start injecting particles on the surface based on the surface charge density. And we keep introducing particles on the charged particles on the surface until the density becomes less than the Goldreich-Julian density, which is the theoretical charge density. This is our result. On the left is the result from Warpex. That's a self-consistent dipole magnetic field that gets built up. And what we have is a disk and a dome configuration. What I mean by that is right along the equator of this pulsar, we have a ring, like a donut ring of positrons, and these electrons are stuck at the pole and they're co-rotating with the pulsar, but there is no emission. So it lands up having this dome and disk configuration. And this is a movie showing how the radial electric field evolves, with the blue being the positrons and red electrons that are emitted from the poles. Actually, this might be a little more clear. And what I want to emphasize here is that along theta equals 55 from the normal, there is no charge at that surface. Let's go back to the theoretical expression for the Goldreich-Julian number density. This is going to go to 0 when 1 minus 3 cos square theta goes to 0, and it will go to 0 when theta equals 55. But when we look at this simulation result from the top, and I let it run longer, and that's the equatorial plane, we do see some structure over there. That structure is a signature for dichotron instability. Dichotron instability is analogous to the Kelvin-Helmholtz instability in fluid mechanics, where we have plasma that is slipping. When we have two layers of plasma that's slipping with different velocities, that leads to that toroidal instability. However, there is a problem. If you look at the boundaries, we have spurious electric fields that have developed. And this is a numerical issue, which we are currently resolving. And our guess or intuition is that as these charged particles are leaving the domain, they deposit their current and their charge on the domain. And that's not being damped out. We need to damp out the current and the charge that it's depositing. We damp out the electric field using the PML, the well-known PML boundary for electromagnetic simulations. And that needs to be fixed. So as soon as the symposium is over, we're going to get to it. But what next in the modeling of pulsars? We have a lot of work to do, and it's really exciting, both numerically as well as physics, as well as the physics aspect. We are pretty satisfied, or we trust that our particle injection at the surface is working correctly, albeit the numerical error at the boundaries. Real pulsars are not aligned. What I mean by that is that rotation axis and the magnetic field are not aligned, they are oblique. So we need to model that oblique pulsar and ensure the particle injection is working even for the realistic pulsar. We want to model, we need to include the QED pair production process both at the pole as well as the equatorial plane, and dynamic mesh refinement. Now, Warpex currently has static mesh refinement for its primary application, which makes sense because they have a the particle accelerator devices are sitting, and we know exactly where to refine before the simulation starts running. But these are cosmic laboratories. They're doing their own thing. So and dynamic mesh refinement is going to be quite challenging to do to ensure that they work correctly. Once we do all of these, we'll be able to study particle acceleration mechanism at this current sheet, and also compare what happens due to the microscale effects with the macroscale effects that are observed for pulsars. Now, this current sheet is very interesting, and what happens in there is interesting even for other astroplasma applications, such as relativistic jets. And so we are collaborating with Cameron and Michael Dawn to study just magnetic reconnection, or just that current sheet, and study what are the key mechanisms by which energy is converted from magnetic field into particle acceleration. And so that mechanism is a key not just for pulsars. And what I'm showing here is our initial setup, where we have the B fields, which are having opposing field lines, and the current here is going into the plane and out of the plane right here. This is our initial setup, and Cameron has made a lot of progress in implementing the relativistic velocity distribution sampling for performing these calculations. Turns out the setup for this magnetic reconnection case is quite challenging, because once we have this, we need to ensure that there's pressure balance across the current sheet. And so what Cameron has done is to ensure this. We have taken this white line across that current sheet and plotted what the total energy density is. Theoretically, this should be a straight line. We're still trying to fix whether our input parameters are correct and how to exactly address this. But once that's done, magnetic reconnection is on its way. With that, I'd like to conclude by saying that pulsars are awesome. They're cosmic lighthouses, but we don't understand why they emit light. For this, we need to perform first principle particle in cell simulations. And typically, the simulations are scaled down. But by scaling down, we change the physics of the problem. And we want to investigate what the effect of that scaling is on predictions. We're going to investigate that using WarpX with dynamic mesh refinement. And we have our first promising result with a little bug. I want to thank everybody who's, Don, Andrew, for collaborating with me, and we've had lots of discussions. So thank you for your contributions on this. I also want to thank Cameron and Michael for magnetic reconnection. Everybody on the WarpX team for all of their inputs. I want to thank David for your valuable suggestions and advice on making this slide. Julianne and her Zen garden. With that, thank you all so much for listening.
Questions?
So after your neutron star setup is all complete, how do you think it would be easier to model other systems, like a black hole or something?
I'm so happy that you asked that question. Yes, the answer to that is yes. Thank you for the question. We actually so WarpX has not been used for astroplasma yet, and these are the first steps towards that direction. But once we have it going for one and magnetic reconnection, we do plan to diversify and do other astroplasma problems that have not been solved because of computational limitations. So, yeah. Yes?
So, you'll be asked appreciative of this question. So the place where you were having charge build up to the boundary, you said when the particles are leaving, they're still dumping their charge. Is that in the PIC method, they're still depositing there? Or is it an effective PML, or is it a bugging particle?
It's not an effect of PML.
Okay.
PML will try to dampen that effect. So PML is actually.
Why are the particles just leaving and taking their charge with them?
In particle in cell, at every grid point, if there's a particle nearby, those particles are going to deposit their charge on the grid. And so they are leaving. They're leaving. We're not modeling what's happening outside over here.
Okay.
So our electric field, typically, we want to dampen that out. It should be an absorbing boundary condition where we absorb even the charges. But it's depositing those charges and it's accumulating those charges.
What I'm struggling to do is I'm trying to understand the mechanism by which it's depositing the charges. How does that happen?
So you say the particles stop moving?
You have the particle near the domain boundary.
Yes.
And in the next step, it's gone. That's not in your listing.
It's gone. But the current.
So what happens between those 2 points that changes the solution so that charge stays around?
So it's deposited its current and its charge, and it's left the boundary. But let's say that the boundary was not there and we had that little buffer region. Then the electric and the self-consistent electric and magnetic fields would try to interact with the particles that are in this buffer region, but we are not modeling those. And in the PML boundary, we are, to prevent electromagnetic waves from getting reflected, we dampen that out. So we are dampening the electric and magnetic fields, but we are not dampening the current that it's depositing on the boundaries.
I get it.
So that's not consistent.
So it's something that's not consistent with the Maxwell equations just by removing a particle and you don't mention current.
That's exactly right. So we have dampened the E and B field, but we have not dampened the current and the charge that it's depositing.
So if you have electrostatics, because the particle's gone in electrostatics, it's gone.
Yeah.
But in your world, there's, right, it's the fact that it's Maxwell is not electrostatic.
Yeah.
Yes, and we are violating Gauss's law there. Thank you for the question.
In other kinds of wave propagation, if you want to have an absorbing boundary, instead of trying to damp things, or in addition to trying to damp things, one can write, for lack of a better, weird integral operators that represent one-way wave propagation, so that you can't have the feedback because it's not in the system.
Right.
Have people tried to do that for Maxwell?
Are you thinking of an analysis what Emmanuel did for the compressible?
No, I'm thinking about like para-axial things from seismology.
Oh.
I know that there are different ways of damping, but I'm not sure whether someone has tried to do the integral method that you were mentioning. I'm not aware.
Okay.
Yeah.
You mentioned that because it's a rotating pulsar, the whole thing changes, and therefore your mesh requirement has to be dynamic in nature. What if you change your frame of reference to be the rotating frame? I'm assuming you fix the rotation. Yeah, the rotation is fixed, but the angular velocity is fixed.
Okay.
So what if you just change your frame of reference to this rotating frame and solve the equations, so that you don't have to do mesh refinement at every step?
They're more for the second order packages, like complicated.
Right.
I would still then have like a moving boundary if I'm. Oh, yeah, I'm in the frame of reference of the. Yeah, I see your question.
So the mesh refinement would stay the same and it's a fixed thing.
Yeah.
Will it work? Or do you think it should be difficult?
So there are some things that I didn't mention here. The rotation period is not always fixed. The pulsar starts slowing down because as the electromagnetic waves carry energy, it's getting its energy from the rotation. And that's how we are going to, what I mean by, when we said that we are going to compare microscale with macroscale, this Poynting flux gives us what is the energy of that electromagnetic wave that's leaving the domain. And that is correlated with how much power that rotation is giving to the EMP field. So that's how we will find out how much the pulsar is slowing down. So what I'm getting to is that if we are rotating with that omega is actually not going to be the same throughout the simulation. The rate of change of omega is negative, it's going to go down. So typically we don't do simulations where we're going with for a pulsar. Plus there are GR effects on at the pole, which we will eventually get to once we've finished those 4 steps.
It is solid body rotation, though, so it's just time varying.
Yes. It's solid body. At least we're treating it as a solid body rotation.
Yeah. Meaning you could make your omega to be also time dependent in that frame of reference.
That's true.
So,
That's true.
I'm just talking about these.
Yeah. It could be done.
You'd still need AMR because you have a large.
We will still need AMR. I think Rithik's point was then we need not have dynamically, we don't need to dynamically evolve the mesh. We can then use static mesh refinement because we are in the frame of reference of the rotating object.
Can you do that with MRX? Or is integrate intrinsically it's dynamic, so you don't really care about that?
Yeah, so something like this is being done for particle accelerator simulations where when a particle bunch, a laser for example, is moving with relativistic speeds, they follow the electron bunch. And so, but then we have to care about Lorentz transformation and we have to back transform all of our data back to the lab frame. And so it depends on what is more expensive, doing this Lorentz transformation and getting all of our ENB fields and back transforming it every time step, or doing a dynamic mesh refinement. So it's both. Yeah. But it's possible. It's just more work.
Thank you.
Thank you.